Hey everybody, this is going to be two problems involving cells with internal resistance. Problem 1, a girl rides a bicycle that is powered by an electric motor. A battery transfers energy to the electric motor. The EMF of the battery is 16 volts, and it can deliver a charge of 43 kilocoulombs when discharging completely from a full charge. The bicycle has a meter that displays the current and the terminal potential difference for the battery when the motor is running. The diagram shows the meter readings at one instant. The EMF of the cell is 16 volts. Determine the internal resistance of the battery and the power dissipated by the internal resistance of the battery. Okay, so remember, our battery is modeled as a resistor in series with a cell. And we also have some external load. In this case, it's going to be the motor. Big R, little r, EMF. We can measure the current, and we can measure the terminal voltage across our battery. But let's just go to the equation that we have. Well, our potential difference is going to be our terminal voltage. Our current is going to be I. The EMF is epsilon. And we want to find the internal resistance and then the power. Okay, so let's write our equation. EMF is equal to I times little r plus big R. Well, we don't know, we want to solve for little r. We know everything but little r and big R. So let's multiply this out. I times little r plus I times big R. Well, I times big R, current times external resistance, is just going to be that terminal voltage. So we can say epsilon is I times little r plus V. We know V, we know I, we know epsilon, our EMF, so we can solve for R. We get epsilon minus V is I times little r. Divide both sides by I, we get R equals epsilon minus V over I. Epsilon is 16 volts. Voltage is our potential difference, 12 volts. And our current is 6.5 amps. So that's 4 over 6.5. 4 over 6.5 is 8 over 13, or 0.615 ohms. That's our internal resistance. Next up, the power dissipated by the internal resistance of the battery. Well, that's just going to be the power across this, the resistor little r. We know power is VI. We could solve for V if we wanted. We know I, or it's V squared over R. Again, we don't know V. Or we could do I squared R. We should do little r because it is little r that we're looking at. Since we already know I and R, we're going to use that. Power is equal to I, which is 6.5 amps squared, times little r, 0.615 ohms. That gives us our power. Plug it into a calculator, we get 26 watts. So terrible P. Power is 26 watts. Okay, that's problem 1. Problem 2, a generator has a terminal voltage of 120 volts when it delivers 13.7 amps and 91 volts when it delivers 22.7 amps. Determine the EMF of the generator. So we know that our terminal voltage is going to change as we change our external resistance. And as we increase the external resistance to infinity, our terminal voltage is going to approach the EMF, which is what we're looking for. If we're thinking about that in terms of current, let's just do a graph of voltage against current. As our external resistance goes to infinity, our current goes to 0, and that's when our voltage is equal to the EMF. So really we want to find, what we're looking for is find terminal voltage V when I equals 0. So what we can do is we can find the rate of change of voltage with respect to current, delta V over delta I. So terminal voltage of 120 volts at 13.7 amps. So 120 volts at 13.7 amps, and 91 volts at 22.7 amps. So that'll basically give us how much voltage change we get for each unit of current change. And it's also going to be the negative of the slope of the graph. 120 minus 91 divided by 13.7 minus 22.7. Actually, it's just the slope of the graph in this case. Negative 3.22 repeating volts per amps. Really, it's units of resistance. And in fact, 3.22 volts per amps is the internal resistance of our object. So if we wanted to, we could use EMF equals I R plus R. Well, we could use that equation. There's a way to manipulate it and get it in terms of voltage. Yeah, since we know a current times resistance would give us 1 voltage, we plug in that current there. Yeah, we could do that. But I'm not going to do that. I'm going to think about this in terms of a graph. So if we have negative 3.22 volts per amp, and let's say we're at 120 volts, how many amps, or sorry, we're at 13.7 amps. How much change do we, let me just write it as an equation. Voltage is equal to negative 3.22 volts per amps times the current plus my EMF. This is just the y equals mx plus b equation for this graph, and I can plug in any set of coordinates for voltage and current. And since this is the equation for this line, I can then use that to solve for EMF. So let's just do 120 volts. 120 volts is negative 3.22 volts per amp. And at 120 volts, we're at 13.7 amps plus our EMF. That's 120 volts is equal to negative 44.144 repeating volts plus epsilon. So our epsilon is just going to be 120 plus that answer. Which is 164.14 repeating volts. So our EMF is then 164 volts. And it's just the y-intercept of that graph again. That's all. 2 problems on EMF and internal resistance of a battery.